So, there's been a lot of experiments that's been done on Fluxgates, double core, ring core, and all these different things. And there's this paper that I found. They have somehow come up with, let's say, a general equation that takes into account everything that we've talked about in the lecture so far. So, what we care about is this second harmonic portion, right? So, and this is just for students to really kind of see how all these different variables interact with each other. Again, the equation itself is not that important, but it's a nice way to kind of give you an idea. Yeah. So here, and again, if students are interested, there's more information in this paper. So what we've learned is T. So what have we learned so far? Here, if you look at this equation, E0 in this case is the even harmonic portion, or rather the second harmonic portion of the output.
What is EP?
EP, it's the, I'm using exactly the symbol that they used in this paper, but that's the excitation.
Okay.
Or the primary voltage. Then you have N, which is the number of turns in the pickup. And then you have NP.
Primary number of turns.
Number of turns in the excitation or primary coil. That's HS is your signal field. And you also have this mu D, which is basically dB over dH in your BH curve. Okay. And there's also mu D dash, which is your second differentiation of your of the BH curve. Okay, a double differentiation. And mu A is the apparent permeability. Okay. I think, Boby, we were discussing before, maybe we should talk about this if there's any confusion. Maybe we can remember this equation.
Oh, okay. So this is the permeability of the core considering the demagnetization.
Correct. This factor here, right? Demagnetization factor.
Yeah. So the mu C here is the relative permeability of the core.
No, mu C or mu A. Yeah.
Oh, okay. Mu A. Yeah.
Yeah. So it could be the mu of the core, the actual
relative permeability.
Relative permeability of the core, or the apparent permeability of the core.
Yeah.
Yeah, that's this one here.
If I had to get actual permeability, then I have to multiply it with mu 0.
Correct. Yes. We forgot to mention that, but yeah, in the equation we said mu R is not just mu R.
Yeah.
Mu R has a relationship here.
Yeah.
But when you plug it back into the equation, then you have
if you want the permeability, as far as relative permeability is concerned, is correct without mu 0.
Yes. Relative permeability is relative permeability.
Yes.
But that's not the actual permeability.
Yeah, it got modified due to that.
Yes.
Yes.
So I mean.
So my doubt is, in this equation, mu 0 is not required there, no?
No, mu 0 is not equal.
Yeah.
Sorry. Because mu 0 is part of the other equation. We just took mu r out.
Yes.
And said mu r is a function of.
Yeah. It's the modified mu r now.
It's a modifier. Yeah, you can. You can obviously rearrange this and get mu r equals. Then you will put it back into the equation, and so it says yes. Yes.
What is HS?
HS is the signal field. So whatever field you're trying to
Measure.
Right. So again, but then what if a student says, "Why do we need to learn all that? Why can't we just use this equation to design a Fluxgate?"
I mean, we need to know how it works.
So is it fair to say if you know how it works, you can just use this equation to?
For example, the sizing of the core,
number of turns.
I mean, how do you excite? How do you measure? Those things are not captured here.
Yes,
correct.
But then I think once you kind of figure all those things out, then just to get an idea how all those fit in.
Yeah.
With what you're trying to measure, yes, it's probably a good equation just to look at.
Yeah.